Hello guys. So today's topic is process state diagram. As you can see, the diagram is displayed on your screen. So let's summarize what we will going to learn. So first thing is process state diagram. Another thing is the terminologies that is used in a process state diagram. And then we will look to the some question that are asked in GATE and uh, these are very important question. So let's move forward to the process state diagram. So process state diagram is basically describes the how CPU handles the process and how a process I mean the uh, throughout the life cycle of process goes. I mean, look at this state. This is the new state. So here we have n number of process. So I can say n processes are there. So n processes are there, and they go to ready state. So in ready state we can have n process. So ready state can have n process. Then after ready state, there is a dispatcher. So dispatcher, the dispatcher has the responsibility to take processes from ready state to running state. So this is running state and this is ready state. Okay, and then if there is some IO request for that process, I mean there are two type of process. So basically, if you can say that. Let me draw this thing. So there are basically two type of processes. So one process is CPU bound. Okay, CPU bounded process, and another process is IO bound process. The process which most of the time requires CPU, that is CPU bound, and the process which most of the time require uh, hardware devices like keyboard. Okay, like you are writing scanf in your code. So scanf will take the uh, input when any user type from keyboard. So this is kind of IO operation. So if your process have multiple number of such instructions, then it is called IO operation process. And in that case, process will go to the will raise a IO request and it will go to the block state. So this is basically what block state. Okay, and after the I mean after block state, if the IO completion, I mean the hardware is granted to the process, if the request complete, it will go to the ready state, and after ready state it will go to the running state. So one thing is clear, that no process can go to the uh, ready state directly if uh, it requires IO request. So if there is IO request, then it has to go from this path. Okay, from this path. And the other thing is, if the process is in block state and IO is not granted, then it will go to the suspend state. Okay, and when the suspend wait, I mean there is some timer. So when the timer completes, then it will again go to the block state and go to the IO completion, and then again go to the ready state. Okay, and one more thing, that if so basically from here to there, I mean this transaction we require short-term scheduler, and this transaction we require long-term scheduler. And one more thing, that if a process is from new to ready state and from ready, if there is some suspension, I mean this process is not in the, I mean the address of this process is more than your physical memory. If your physical memory is of 32-bit, but if the process require more bits, then it will go to the your virtual memory. Like, so if process size is 38-bit, let's say, so for more 6-bit it has to make a virtual memory. So virtual memory, this process will suspend, and it will go to the suspend ready state if it gets the 38-bit size of virtual address. Then it will resume, and then the other steps will presume. So if I have written here, like you can see there. So you can see I have written it is placed onto the external storage. So external storage means it requires some uh, uh, like hard disk space or anything, because whenever there is virtual address kind of thing, it will go to the hard disk. So this is for virtual address. Okay, so when it goes to the suspend ready state, if it requires external storage, then it will go to the suspend ready state. So this, I mean this work is done by midterm scheduler, that is called MTS. Okay, and here you can see if IO is not granted, it will go to the suspend wait. If IO request complete, then it go to the resume state. But if IO completed but is still suspend state, then it will not go to the wait state, it will go to the suspend ready state, and from here it can go to the ready state. So this is basically a process state diagram, and after the completion of process it can terminate. Okay, so you guys can note this down. And this is very important. So what I'm doing, I'm just erasing everything that I have written, so that uh, you guys can see the diagram clearly. And yes, this is a basically process state diagram, and there are some terminologies that I have mentioned, like now long-term scheduler, short-term scheduler, mid-term scheduler, and other things. So let's move forward to those topic, because those are also very important. I'm just moving forward to the topics. So basically, this is long-term scheduler, and it is related to the performance of the system. So long-term scheduler is directly connected to the performance areas of your system, and it decides the degree of multi-programming. This is a term, degree of multi-programming. So this is degree of multi-programming means if there are uh, your degree of multi-programming is 100, then at that time 100 process can reside in your ready state. Okay, so this is basically the degree of multi-programming. Okay, so how many process should reside in the ready state? Long-term scheduler decides that. And uh, next topic is midterm scheduler. So midterm scheduler means just that I have mentioned above. As you can see that midterm scheduler, this is the responsibility of midterm scheduler. This is a part of midterm scheduler. You can see this is midterm scheduler. So midterm scheduler just takes the responsibility of suspension of the process, and if any process requires extra bit of memory, it will go to the ROM. As I mentioned that it wants some virtual memory, it will go to the ROM. So from RAM to ROM or ROM to RAM, it means the process of initiating the suspension state, and when it is completed, the virtual address process, it will again back to the ready state. So from RAM to ROM and ROM to RAM, middle term scheduler is responsible for that. And now next is short-term scheduler. It is very important. So it just controls the context switching, and it decided which process should execute next, and it will then call the dispatcher. And if you want to see what dispatcher, uh, what is the work of dispatcher, so say a process P1, and if you I will upload the video for computer organization, then we will understand there is a program counter which stores the address of next process to be executed. So address of next uh, process uh, in execution, I can say. So what P1 has some uh, program counter which wants after P1 which process to execute. But At that time you just preempt this process and you go to the P2. Then what happened? Dispatcher just save the state of P1. Like I mean P1, if P1 is a process and it has three steps, and currently it is at step 1, at the end of step 1, and you just from there you preempted this process and you are going to execute P2. Okay, so what happens, it will store the state of P1 that it is executed till this step, and when it resumes it should execute from step number 2. So dispatcher just save the state of current process, and dispatcher just uh, reload the state of next, I mean the next process that that is going from ready to running state. So it just store the state of past process. Okay, and just store the state of future process, you can say. So this is the work of dispatcher. So what short-term scheduler uh, uh, does, it just calls dispatcher. And now moving forward, I think this is the end for process state diagram. And now moving forward to the questions that were asked in gate. I don't know the year of these questions, but these were asked in gate. These two questions are very important. So the first question is, so I'm going to solve this question. Okay, so the first question is, in the following process diagram, this is the diagram of uniprocessor. Just see this uniprocessor system. I mean it is not a multiprocessor. Assume that there are always some process in ready state. Always there are some process in ready state. Okay, so some process, let's say X process. And now consider the following statement. Okay, if a process make a transaction D, I mean it is just going from running to termination, this is transaction D, then it would result another process making the transaction A. So this transaction actually does not depend on this transaction, because this is how a short-term scheduler is managing from ready to running state. This is not dependent on this transaction. So this is independent of D. So transaction A is independent of D, because from ready to running and from start to ready, these are the responsibilities of short-term and long-term scheduler respectively. So this is not the this does not affect on transaction D. Uh, so this statement is wrong actually. So we can say this is not a correct statement. Now moving to the next statement. A process P2 is in block state and can make transaction E. So is in block state and can make transaction E, while another process P1 is in running state. So another process P1 is in running state. Yes, running means it CPU has been granted to this process. So yes, if any process is in running state and here there are some IO request and IO request is completed, then it will go to the ready state. So this is not actually dependable. Again, these two are transaction are independent. So this step is correct. And the third thing is the OS uses preemptive scheduling. So guys, uh, whenever there is a transaction from running to ready state, there is always a preemptive scheduling, because while a process is in running state, you are just preempting it and again sending it back to the ready state. So it is uh, preemptive transaction, I can say. Okay, so yes, this is correct. And OS uses non-preemptive. No, this is not correct. If the C transaction were not given, then yes, this step would be correct. So the correct statement, the correct answer is C. Now moving to the next question. I hope you guys understood this question. Again, this question. These actually in this question, you can say that this is a new state. Okay, so I can write new. Okay, and this is basically a ready state. I can write ready here. This is basically a running state. This is the last state that we can call termination state, and this is basically a, you can say, the blocking or waiting state. Okay, so what it is saying, it is saying identify the false state. So it is, first statement is, it is multi-programming, multitasking operating system. So yeah, at the time multiple tasks are being done. So yes, this, I think this statement is correct. So let me correct this statement. So this is correct, but uh, it is asking false. So this is actually correct, first statement. And it uses preemptive scheduling. Yes, it is using no, because there is no transaction from running to ready state. I mean, no transaction there, so it is not using preemptive. So this is wrong, and it is not possible to reduce the degree of multi-programming. Uh, Actually, degree of multi-programming depends on how many number of processes are there in ready state. So it is possible to reduce the degree of multi-programming if you can send the process from ready to suspension state, then degree of multi-programming can be reduced. So if, let's say there are 10 processes in ready state, and let's say you are sending two of uh, them from ready to running, ready to suspend state, then there would be 8 processes are there in ready state, and the number of process which are present in ready state are actually the degree of multi-programming. So you can reduce the degree of multi-programming, or you can send back from suspension to ready state. Okay, and you can increase. So looking at this diagram, it is possible. So it is not possible to reduce the, so okay guys, so here it is written it is not possible. So guys, here you are not seeing any such suspension state that I have mentioned above. Like looking at the process state diagram again, if you guys can see the diagram, there is a state like this, suspension ready. So in the question, the diagram is, in the diagram question, the mentioned diagram, there is no suspension ready state. So yes, we cannot reduce degree of multi-program because no suspension state. If there would be suspension state, then we could reduce the degree of multi-program, but at this time we cannot. So yes, this statement is always correct, because it is saying that we cannot, so it is not possible. So far second statement is not correct, so it asks the false statement. The answer would be B. So answer would be B. Okay guys, I hope you guys enjoy the video. If video is correct and you understood everything about process state diagram, then please comment and share. Thank you.